In this web lecture video, we will present Digital Innovation Hub activities at Josef Stefan Institute. Let's first look at our department with a focus on Agile Manufacturing. The Department of Automatics, Biocybernetics and Robotics is part of Josef Stefan Institute in Ljubljana, Slovenia. While we conduct basic and applied research in multiple various areas, we will focus on topics related to Agile Manufacturing. Most related area of research at our department is industrial automation. In this area, we conduct basic and applied research in the area of factories of the future and industrial automation. One of our goals is to expand the field of industrial automation through passive and active reconfiguration, modular design of software and hardware architecture, implementation of easy-to-use robot programming, and implementation of digital twins. In the area of humanoid and cognitive robotics, we focus on the development of new technologies for robotic systems that can operate in natural environments and in collaboration with people, with a focus on industrial settings. This is only possible with robots that can continuously and autonomously acquire new sensory-motor behavior and higher level knowledge. Humanoid robots are, due to their similarity to humans, especially suitable for operations in environments shared with people. The humanoid robot Talos was designed with an industrial setting in mind. The aspect of collaboration, an integral part of factories of the future, is further studied in the area of collaborative robotics. Here we use integrative approach of robotics and machine learning to investigate and study collaborative robot behaviors in physical human-robot interaction scenarios. The study of human-robot collaborating is enhanced by study of human-human and robot-robot collaboration. In this section, we will focus on a general overview of the Digital Innovation Hub at our institute. Josef Stefan Institute is the Digital Innovation Hub coordinated by the Inner Center for Technology Transfer and Innovation. Based on European integration within the European Commission's Digital Innovation Network, the Hub is participating in applications for European Commission's projects for digital innovation hubs, in applications for projects where the component of the Digital Innovation Hub is required, and in applications of the letter of intent on various initiatives for digital innovation hubs. As the central part of development, digitalization, and industrial relations at national and international level, the Hub is establishing a system of collaboration between the JSI research departments, the domestic and foreign economy, and the partner networks within the Enterprise Europe network and the network of technology transfer offices. The Hub helps researchers and companies to innovate, to transfer scientific results into practice, and digitalization of industry within the framework of a network of competence centers across the European Union. The Hub provides one-stop shops and cross-border technology transfer services in the EU and serves as a contact point for the local ecosystem in Slovenia. Let's look at more specific Digital Innovation Hub activities and related activities we carry out at our department. In the field of education, training, and knowledge transfer, we offer PhD education programs, including young researcher programs. We offer lifelong learning and workforce training. We also focus on popularization of science through open door days and media coverage. We offer collaboration through research projects, funded either locally or by European funding. Over the years, we participated and led a number of industry-oriented projects. The consortium, in majority of them, included industrial partners from the local area and throughout Europe. We also offer a variety of activities in the field of lab testing and infrastructure leasing services. We offer ideas management and materialization in the form of ideas generation, assessment, feasibility study, or technology readiness assessment. We offer technical support on scale-up through concept validation and prototyping. In the field of verification and validation, we offer product demonstration. In decision making, we help with decision support and development, and in the physical human action and interaction, we offer collaborative intelligence or feedback loop. We will now present some specific example activities at our department related to Agile Manufacturing. In the RobConcept project, we collaborated on development of a robot-aided quality inspection of household machines using a collaborative robot. Quality inspection of final products is becoming an increasingly important factor in improving competitiveness in household appliance manufacturing. A robotic cell concept for quality inspection of household appliances, which is used as an end-of-line inspection system, was designed. We mainly focused on those inspection processes where the interaction of the robot with the products is crucial. In the case of household appliances, this is primarily the inspection of buttons and knobs. We proposed inspection procedures that use the robot's internal torque sensors. A parametric approximation of the measured torque based on radial basis functions was used to identify the faulty products. The criteria for defect detection are based on changes in forces and torques. Experiments on real devices have shown the success of the proposed method. Using a Franca Amica Panda collaborative robot, we can successfully replace a human operator for quality inspection. The robot is used to manipulate sensors such as camera and for the manipulative task required for the product's functional testing. Besides, some inspection procedures are performed directly by the robot. In doing so, we take advantage of the flexibility and versatility provided by the collaborative robots. In the quality inspection of household appliances, especially for the inspection of buttons, we use internal joint torque sensors of the robot. As mentioned, experiments on real appliances have verified the efficiency of the proposed methods and classification of potential defective elements. In collaboration with an industrial partner, a prototyping project to improve a gearbox design was carried out. The goal was to design and test a gearbox with the possibility of torque measurements of the part itself. After an initial research into existing solutions and patents, 4 possible methods for torque measurements were identified: measure strips, surface acoustic waves, rotational encoders, and magnetostriction. Based on several factors, the prevailing one being cost, measure strips were selected. To determine optional positioning for selected torque sensors and to optimize this design, the deformation of the transition housing was analyzed in simulation. We analyzed the part under shear, torsional, transverse, and bending stress. Even though some areas of the housing was defined as the possibility of sensor locations, we determined the signals would be too weak to get an actual measurement. So in the next step, we looked at the pin deformations. We looked at the deformations of these pins in the transition cage. The analysis provided the optional number of pins for measuring purposes and locations for measuring strips. Based on these results, we defined 4 possible design concepts and compared them via evaluation. The best suited one was selected for physical prototyping. In the next step, the prototype was constructed. An evaluation environment was also defined and built. Multiple sensors were employed on the prototype itself and in the evaluation environment. Multiple measurements were carried out from shear, torsional, transverse, and bending stress to temperature dependencies. These measurements from real life were compared to previous ones gained from simulation. The complete results showed the validity of our proposed design. In the end, electronic components were designed and produced. Let's look at the last example activity regarding Agile Manufacturing. We collaborated with a robot company to develop a skill library for transfer of complex tasks. The project was motivated by the need for automation of finishing operations, such as polishing and grinding, on contemporary industrial robots. Existing approaches are both too complex and too time-consuming to be applied in flexible and small-scale production which often requires the frequent deployment of new applications. Our approach is based on programming by demonstration and enables the programming of finishing operations also for users who are not specialists in robot programming. Several different approaches were used to capture human demonstrations: digitizers, manual robot guidance, and marker-based vision systems. Programming by demonstration is especially useful for teaching finishing operations because it enables the transfer of expert knowledge about finishing skills to robots without providing lengthy test descriptors or manual coding. Besides the human demonstration of the desired operation, the proposed approach also requires the availability of the kinematic model for the machine tool applied to carry out the finishing operations. The transferred skill can be further improved through force-based learning and virtual mechanisms. Several practical examples of grinding and polishing tools were integrated during the project. Another feature of the proposed system is that the user demonstrations of finishing operations can be transferred between different combinations of robots and machine tools. At the end, let us briefly present the demonstrators we're developing under the Trinity project at our department. The ability to reconfigure production cells is crucial for agile production processes where production frequently changes from one product to another. In this demonstrator, we develop a robotic work cell that includes hardware components with passive degrees of freedom to enable quick robot-supported reconfiguration from one product to another without any manual intervention. The developed robot work cell is a reconfigurable manufacturing system suitable not only for large production lines, but also for low-volume, high-diversity production. The developed system enables quick setup and short reconfiguration time with a minimum of intervention by human workers. It offers software and hardware reconfiguration tools that can be used also by users without in-depth expert knowledge. However, if the production task requires new capabilities or modules, users with more in-depth knowledge can develop new software and hardware components without disrupting the already defined work cell architecture. This is due to the modularity and tight integration of both software and hardware elements of the work cell. The developed work cell can be used in any sector that requires automated assembly of a variety of products that change frequently. Some example areas where the proposed reconfigurable cell was implemented and evaluated covers areas from automotive industry, furniture industry, electronic industry, etc. In the automotive industry, for example, the cell was used to implement the assembly of various automotive light housings. The original standard production line consists of specially designed assembly machines different for each light housing model. While these machines provide an assembly method with short cycle times, they are not cost efficient as they have to be designed and produced for each different light housing model. To ensure the possibility of assembly of various light housings from a family of products in a single work cell, the developed work cell focuses on reconfiguration of housing fixtures within the cell. The presented use case, titled Efficient Programming of Robot Tasks by Human Demonstration, aims to release the burden of traditional robot programming. It addresses the challenges of robot programming by providing software and hardware frameworks to integrate programming by demonstration paradigm into an effective system for programming of industrial production tasks. For example, automated robot assembly, finishing operations by manual tasks, robot motion for vision control, etc. In this demonstrator, we provide effective user interfaces for programming by demonstration in industrial environments for a variety of systems. They can be used for the specification of robot operation in industrial production tasks. The demonstrator shows that robot programming by demonstration is a viable paradigm to improve the programming of classic industrial production tasks, such as autonomous robot assembly, as well as tasks that are rarely automated in industrial production, for example, finishing operations and bimanual tasks that include force control. The proposed approach can be used in any sector where new robot tasks change often, or there is a need to speed up or ease the robot programming process. Some example areas where this approach was implemented and provided benefit was furniture industry, automotive industry, shoe industry, etc. Thank you for watching the video about Digital Innovation Hub services and related activities we carry out at Jože Stefan Institute.